This is Astrophysics, this is Telescopes Lesson 3, and this is the Rayleigh Criterion. So the Rayleigh Criterion states that the resolution of 2-point objects is not possible if any part of the central maximum of either image lies inside the first minimum ring of the other image. So with light of wavelength lambda and an aperture of diameter d, the minimum angular separation that can just be resolved is given approximately by this. So the Rayleigh criterion is approximately equal to the wavelength divided by the diameter. Oh, by the way, theta is always in radians, so angles are in radians. So two stars there, they'd be basically just about be able to make them out. But they both lie within the, about to lie within the first minimum, so they wouldn't be visible. Here's a real life example of the Rayleigh criterion. So the image on the left, the ground-based image, which is in Washington, the Rayleigh criterion's not enough to distinguish between two separate objects, whereas the Hubble Space Telescope can actually clearly see that there's two distinct objects next to each other. Part of that's down to the Rayleigh criterion, but also because the Hubble Space Telescope's in space, it's not subject to any atmospheric smearing. All right, let's move on. So let's just do straightforward question, comparing optical devices. Right, so we're going to calculate the Rayleigh criterion angle for the following devices with light of wavelength 500 nanometers. So if you want to have a go at this first, and then I'll take you through the answers. It's really straightforward. So the light's always 500 nanometers, and we've got some different apertures with different diameters. So straightforward. So the Rayleigh criterion angle is equal to wavelength divided by the diameter for each one. So A, human eye, so that's going to be 500 nanometers, so 5 times 10 to the minus 7, or 500 times 10 to the minus 9, divided by 8 millimeters, which is 0.008. So that gives us the human eye at 6.3 times 10 to the power minus 5 radians. Then B. So cheap telescope, again lambda over d, 500 times 10 to the minus 9, divided by 5 centimeters, so 0.05. That'll give you 1 times 10 to the minus 5 radians. C. Expensive telescope, again 500 times 10 to the minus 9, divided by, this time it's 0.2. So a more expensive telescope's giving us 2.5 times 10 to the minus 6 radians. And then D, 500 to the minus 9, divided by 2.4 meters. These are all approximately, I shouldn't really be writing equals, should be approximate. Approximately equal to 2.1 times 10 to the minus 7 radians. So you probably figured out by now that theta is inversely proportional to the diameter. So the larger the diameter of the aperture, the smaller the Rayleigh criterion. And the smaller the Rayleigh criterion, typically the better the telescope will be. Definitely resolving between two separate objects at a great distance. So this one, the moon crater question, this is a very typical exam style question. There's bits of this that I've not explicitly shown you how to do, but I'm going to let you have a go at it. So obviously pause and attempt it. I will tell you that you will need to use an equation from further mechanics in physics. Alright, I'll take you through the answer. So a terrestrial telescope has an objective diameter of 15 centimeters, has a resolving power reduced by, this is what I mentioned earlier, atmospheric smearing by a factor of 5. Calculate the smallest diameter of crater it can resolve on the moon with light of wavelength 500 nanometers. And the distance to the moon, 308,000 or 3.8 times 10 to the 8 meters. All right, let's have a look. So first of all, we need the Rayleigh criterion. So that's simply the wavelength divided by the diameter of the aperture. So the wavelength again, 500 nanometers. So 500 times 10 to the power minus 9. Divided by the diameter, which is 15 centimeters. So 0.15 meters. So that gives us a Rayleigh criterion of 3.33 times 10 to the minus 6 radians. So we can deal with the atmospheric smearing straight away. So the resolution angle, the Rayleigh criterion, will actually increase by a factor of 5. So what we need to do is 5 times 3.33 times 10 to the minus 6. So the resolution that we're actually dealing with is approximately 1.67 times 10 to the minus 5 radians. So I told you that you'd need an equation from further mechanics. And what we need to do is this. So we're looking for this arc length. This arc length, remember, is S, because the angle is in radians, theta. And the moon distance we can just call radius or distance. And if you remember, S is equal to r theta. Or more typically, you might have been taught as theta is S over r when you did circular motion. Angle obviously in radians. So the arc length is equal to the distance r multiplied by the angle in radians. So distance is 3.8 times 10 to the 8 meters multiplied by the Rayleigh criterion angle, which is 1.67 times 10 to the minus 5 radians. So that gives us a crater diameter that we can see. Put that in your calculator. 6,333 meters. Or 6.3 kilometers. Hopefully that one went okay. If you got it wrong, just rewind, attempt it again. And thanks for watching. In the next lesson we'll look at collecting power and then we'll compare telescopes. Thanks.